Okay, so once again, we're welcome to physics class. Today we're going to look at the generator, the AC generator. Okay, when you say AC, you can see alternating current. AC means alternating current. So today we're looking at what we call the AC generator. A generator is an electromagnetic device that is capable of turning rotations or force into electrical energy. So it's like an electromagnetic device, electromagnetic. So you can see the first connotation, you can see the first terminology. It's an electromagnetic. There's electrical, there's magnetic effect. So it's an electromagnetic device that is capable of turning the force or motion into electricity. So something that can harvest motion, rotation, force into producing electrical energy is called, such an electromagnetic device is called a generator. Such an electromagnetic device is called a generator. So without much ado, let's look at the basic concept of a generator, the effect. The generator effect is used to generate an AC alternator. An alternator is like a bigger generator that is used in power station. Okay, it's a generator that is used to produce AC current or EMF, electromagnetic force in a power station. Now, a simple alternator is a type of generator. We already say an alternator is a generator, right? That is used in power station. A simple alternator is a type of generator that converts mechanical energy to electrical energy to form an alternating current, right? Now, what do we mean by mechanical energy to electrical energy? Like I said, when I started, I said generator is an electromagnetic device that is capable of converting movement. Movement is mechanical energy, okay? Movement, kinetic. Movement is mechanical. So when you're dealing with movement, force, motion, movement, this is mechanical. So the ability to convert motion of what? Motion of rotating coil, the force that's produced when the coil rotates in between magnets. So that motion is being harvested, is being harnessed, is being converted into electrical energy. What is the electrical energy? Because it induces an EMF or it produces an alternating current. That alternating current or EMF that is induced is called the electrical energy. The force and the motion is mechanical energy that is being turned. For example, when you studied the mechanical energy, we divided them in mechanics. When you study mechanics, when we studied energy, we divided mechanical energy to two forms. We say potential energy and kinetic energy. So anything potential energy, when the energy you have when you are in a stationary position is potential energy. Even potential energy, we divided it to like 2 or 3. We say we have the gravitational potential energy, the energy you have when you're in a high position, like you're in your balcony, the energy you have in a high position, you climb the top of mountains, or the energy you have when you're in a cliff, the energy you have when you are rooftop. All these are gravitational potential energy. This energy, they are mechanical energy. They are forms of mechanical energy. The energy also from strain is also mechanical energy. Now, both mechanical energy, which is energy an object have at rest or in stationary position, is called mechanical energy. Another type of mechanical energy is kinetic energy. The energy you have when you are moving around your house. When you're doing busybody, when you're moving up and down, you're not stationary, you're not in one place. Instead of focusing, you're not focusing, you're moving, you want to drink water, you want to... all this energy you have when you're moving around, or you go and ride bicycle downstairs, you go anywhere. These energies that you have, they're called what? They're called kinetic energy. And these kinetic energy are also forms of mechanical energy. So Here we've itemized mechanical energy and we've talked about it extensively. Now we say generators are those electromagnetic devices that are capable of converting this mechanical energy into what? Electrical energy. Into electrical energy. Now what are this electrical energy? The induced EMF. The induced EMF or induced alternating current. The induced alternating current, they are called the electrical energy. So a device, a machine, electromagnetic machine. Why is it electromagnetic? Because we have magnets and we have coils, wires that are wounded rounds. They are called coil, like you see in this figure. Okay, now you have coils that are arranged in rectangular array. Okay, that are arranged in rectangular arrays in multiple forms. Okay, to create a rotation, or that enable a rotation and create electricity. And we can see this with a galvanometer or a meter, any meter, ammeter, galvanometer, any of these meter that measures current or induced EMF, voltmeter, whatever that measures any of this. Okay, the induced EMF, which is voltage, or the induced current, which is being measured by ammeter or galvanometer, and so on and so forth. So this result, the output is electrical energy. The input is what? Mechanical. Now in everyday generator, the one you have at home, if you have a generator, we rotate it. This is a rod. There's a rod here that is connected to this slip ring commutator. We have two slip ring commutator. These two yellow roundish color, yellowish orange color. These two orange color, they round in circular form. But if you look at them very well, there is a gap between a vertical gap between the two commutator, slip ring commutator. Attached to the slip ring commutator are two carbon brushes. Why do we call them carbon brushes? Okay, we call this rectangular one, this rectangular a bit darker, or this is no more orange. This could be called a brownish color or something. Okay, these two rectangular one, they are called the carbon brushes. These two carbon brushes connect to the slip ring commutator, and the slip ring commutator rotates with the coil. The coil, this rectangular coil, this rectangular coil, they rotate. Okay, they rotate. They connected to the rod, to this slip ring commutator. They're connected to this slip ring. This slip ring, they're circular. They're all cylindrical. They're circular or cylindrical in shape. Okay, they rotate with the coil. Okay, but when they reach, you see this, there's a gap here in the vertical. If you look at it, on top of it and at the bottom of it. At the bottom of the slip ring commutator. Why we call it slip? Because there's a slip between them. There's a gap. That's why we call it slip ring commutator. Otherwise, we could have just called them commutators. Okay? They ring. They're circular. That's why we call them rings. Okay? That's why we call them rings. So, there's a gap. There's a slip. There's a gap between this commutator, such that when it rotates at 90 degrees, this gap will be touching the carbon brushes side, so there will be no contact. The carbon brushes will be in empty space. It will be on this empty space at 90-degree rotation, so there will be no current contact. But the torque that is already produced, the capacity of rotation that has been created, the force, the torque is like the force, torque, T-O, this torque, the torque that is created. I want to show you what I mean, the spelling of a torque. Torque. This torque. This torque is a force. You know, anything that is rotating, a huge force has been created to enable it to rotate. A huge force has been created to enable it to rotate. So when it reaches, when this reaches this point, when this slip ring, this gap reaches the carbon brushes, when it's at this point, there is no contact anymore. There's no contact because it's now, the carbon brushes is now exposed to the open space. The open space at 90 degrees. Okay, it's not exposed to, so there's no force at all. Now what keeps it going is the torque. Torque that has been created that keeps it to rotate. Okay, till it passes this gap. Till it rotates past this gap, and then the force will continue again. Now this is a rod. It's shown with the broken lines. Tiny broken lines. you can see there's a rotational arrow shown that is rotating clockwise. And these rectangles, they are coils. The more the number of turns you make, the more the induced EMF will be. I have more magnitude. The bigger the induced EMF, the more the magnitude of the induced EMF. The more this one you create, the more the strength of the current created. And the more or the stronger the magnet you use also, the bigger the magnetic field and the bigger the induced EMF or the induced current, alternating current that is produced in this system. In a nutshell, a generator does, or like when we study electric motor, a generator does not have, we don't connect to a battery. In a generator, we don't use battery, we don't provide the electrical energy. In electric motor, we provide electrical energy, like in a drilling machine, hair dryers. The hair dryers you use at home to dry your hair. The one we use when you get to a restaurant, after washing your hand, you put your hand to dry it. To dry your hands, we have machines now. These are motors. These are electric motors. But for generator, no. And for generator, we don't plug them to electricity. For generator, we don't plug them to electricity, but we create a force that produces electricity. We create a mechanical energy. Mechanical energy could be in the form of force, it could be in the form of kinetic energy, which is the motion that you've created. The motion you've created is the kinetic energy. And this kinetic energy will help to rotate the coils. And this coil, as they rotate, what happens is that, there's magnetic field. Anytime you have a North Pole magnet and a South Pole magnet, magnetic fields are created. Okay, anytime you have two magnets, a North Pole and a South Pole, magnetic fields are created. And once there are magnetic fields and there are wires like coils, coil is wire that is wounded round, okay, multiple number of times probably. Once there are coils or solenoid that will be created in between two magnets, and it rotates, now it's horizontal. There will be no current produced at this point. There's no current produced here. Because why? The horizontal and the magnetic fields are also horizontal. There's no induced EMF. But the moment this coil rotates to 90 and becomes vertical, the orientation of the coil becomes vertical. Once this, now the orientation of the coil is horizontal. Once it becomes vertical, like this way become the top, standing vertically, and this way become the bottom, standing vertically, then the magnetic field will be cut across the coil, across the wire. Okay, once fields are cut across the wires, EMF will be induced. According to Faraday's law of electromagnetic induction, okay, EMF will be induced. And the direction of the current is given by the Lenz's law. Okay, that the induced EMF is always opposite the direction of the effect that is producing it. That's Lenz's law. But for Faraday's law, it's talking about the magnitude of the induced EMF, the magnitude, the size of the induced EMF, the factor responsible for the size of the induced EMF. Okay, so that's Faraday's law. So the law of electromagnet is that once we have a force produced and the coil has been made at 90 degrees to the magnetic field, the EMF will be induced. Once the force or the coil is oriented at 90 degrees to the direction of the horizontal magnetic field, these are the magnetic field, these tiny blue lines with arrow. These tiny blue lines with arrows, they are the magnetic field that are emanating from the north pole of the magnet. This is the north pole of the magnet towards the south pole of the magnet. These two polarities, they have a force, a characteristic force, which starts from the north and goes to the south. So once you have that, and you have a coil that is rotating, and at 90 degrees to this magnetic field, EMF will be induced or current will be produced. And that current can be seen using connected to a galvanometer. A galvanometer deflection will show you that a current has been produced and an alternative voltage or alternating current has been produced. Okay, so this is a generator. This is the symbolic representation of a generator. The simple way how a generator works. So we can all produce a generator, all of us. We can. You just to get the materials. One, you need two magnets, a north pole and a south pole. Two, you need to wound your coil in a rectangular manner, multiple number of times, so many times in between. You need to buy the slippery commutator, okay, two slippery commutator. You need to buy a rod that you connect to the slippery commutator. Okay, the rod, once it's connected to the slip ring, you attach it to the slip ring commutator. This, see, at this point it's attached here. And then this rod, you have something that you can tie it to it, like a rope, to draw it and make it start to rotate. Okay, like a rope or anything that you can, like a belt that you can use to circle at this point and draw it to cause this rod to rotate. Once the rod is rotating, the coil will be rotating and the slip ring will be rotating. Okay, the coil and the slip ring will be rotating, and when they are 90 degrees to the orientation of the magnetic field, EMF will be induced according to Faraday's law of electromagnetic induction. So I hope this point is clear, and then we move to the next one. Let's take a look at some theoretical, whatever they're going to say here is what I have explained already. We've talked about the rectangular coils. You make the coils to be in rectangular form, like as shown in this diagram. You make them a lot in this rectangular form. Okay, and then you allow them to rotate in this magnetic field arena. You allow this rectangular coil together alongside with the slip ring commutator to rotate within this sphere, this magnetic field arena. Is okay? So, and then the coil is connected to center ring emitter to metal carbon brushes. We already explained the carbon brushes. The carbon brushes allows the current to continue, okay, to flow. Okay, the current that is produced to flow and can be measured here, and it continues, a continuous process. The slip ring commutator also rotates and provide that necessary motion that is needed. The slip rings and the carbon brushes, they provide the connections between the coil and the meter. These two, they connect this meter. You can use any meter. Like I say, it can be an ammeter, a galvanometer. Galvanometer is for small current deflection. We use galvanometer for small current deflection. If you know the current that it produces is big, you can use what? An ammeter. If it's big, if it's the EMF that is produced, that is induced in this regard, you use a voltmeter. So you just call a meter a multimeter. Okay, it could be a digital multimeter, anything you can connect to it to measure what is being produced, Is that okay? So what the job of the carbon brushes and the slip ring is to allow the continuation of what is in this rectangular array of the coil to be continued to the meter. Like it allows the continuation of what is coming from here, what is be produced, the current that is produced from this sphere, to be forwarded or to be moved to the meter so that we can read it from the meter. So it's like allow the journey to continue. This slip ring commutator and the carbon brushes, they both allow the journey to continue. But that's not the only job they do. Now, when the coil turns in one direction, what happens? The pointer deflects first. So what happens is that when the coil turns in one direction, 90 degrees, the pointer will deflect to one direction, maybe to the right. And then, after 180 degrees, it changes direction again. Then it deflects to the other side. The pointer deflects to the left side. So that you can see here, this pointer from the meter is deflected to the right and also deflected to the left. So it's because the current changes, reverses, and so it's also shown in the meter. Is that okay? So we say when the pointer deflects first, we say when the coil turns in one direction, the pointer deflects first one way and then the opposite way. First it deflects one way and then the opposite, and then back again, and then the process will continue in that manner. This is because the coil comes through the magnetic field lines and an EMF, and therefore current is induced in the coil. EMF or current is induced in the coil. Okay, I showed the relationship between current and EMF. EMF is voltage, so V is equal, according to Ohm's law, V equals to IR, according to Ohm's law. Okay, the I is the current, this I is the current, and this V is the EMF or the voltage or potential difference. So there are three names for this. We can call it the voltage. This V is voltage. Okay, you can call V voltage, and you can call it potential difference. You can call it a potential difference. So we either use this name voltage or PD, potential difference, and let me abbreviate it, we call it PD, potential difference, or we can call it an EMF, electromotive force. EMF is electromotive force. Okay, whether we use the term electromotive force, or we use PD, potential difference, or we use voltage, we're technically referring to the same thing. Then the current is what flows in a wire that you don't see. The current is what flows in a wire that you don't see, okay? And if you multiply by the resistance of the wire, R is the resistance of the conductor that you're using. If you are using a wire, you multiply by the resistance of the wire. If you're using a bulb, okay, you multiply by the resistance of the bulb. So if you multiply the current and the resistance of the bulb, you get the voltage, V. You get the voltage. Voltage is the one that glows. When your bulb lights up, what you see is the voltage. When your bulb lights up, what you see is the voltage. The one that glows is the voltage. The current, you don't see it. Okay, you don't see the current. The current is only flowing in the wire. Is that okay? Okay, so let's move on to our generator effect. Now the pointer deflects in both directions because the current in the circuit repeatedly changes direction as the coil spins. So as this coil is spinning, okay, it will reach certain level, then it change direction of rotation. It change direction of rotation. When this one twango, okay, we're going to show it. Okay, we're going to see it. Is that okay? How it changes direction, we're going to show it. Is that okay? So that's for that first part. Now let's move a bit down. Motors and generators look very similar, but they do very different things, right? If you look at their diagram, they do very different things. They look similar, but they do different things. Now, but the difference is that in motor, we put a battery here. We connect with a battery. So when we connect with the battery supply electricity to produce motion. The work they do is actually opposite. For motor, it is it converts, excuse me, okay, 1 minute, just excuse me. For motor, it converts electrical energy to mechanical energy. For motor, it's like vice versa. For motor, it converts electrical energy to mechanical energy. For generator, it converts mechanical to electrical. You see, they are opposite. The job they do is opposite. Okay, now let's go to the graph of AC generator. Let's take a look at the graph. In the rotation, how current reaches the peak, or the voltage, how it reaches its peak, okay, and then come down to zero, and then reach the negative side, and then like that. So we go to like when do we have the peak, when do we have, so this is what we want to look during the rotation of the coils in this magnetic field arena. During the rotation of the coil and the slippery commutator and the slippery commutator, then what is produced, how the EMF or the voltage that is produced or current that is produced, the journey of it is what we are looking at in this graph. The journey is what we're going to look at in this graph. Now, we say AC generator creates alternating current, produces current. Every generator, AC generator, alternating current generator, they produce alternating current. Now, it varies in size and direction as the coil rotates, right? It depends on the coil that you've made available and the strength of your magnet. The strength of your magnet, the number of size of your coil that you've created, rectangular coil that you've created, the more the number of turns, the more the induced EMF. The stronger the magnet, the more the induced EMF, and so on and so forth. Okay, so now at this journey, what happens? How is this graph produced, or what is happening that results to this graph? We said the size of the induced EMF depends on the number of the field lines that it cuts. Also, how much field lines. Now, how much field line depends on the strength of the magnet. The field lines, the magnetic field lines, depend on the strength of the magnet. If you bring weak magnet, the field that will be produced are small, and they're a bit like further apart. They're small. They're not a lot. Okay, but if you bring a stronger magnet, then there will be more field lines. The more the field lines, then the more the induced EMF. Because when the coil rotates, at 90 it cuts it will cut across the magnetic field line. And once magnetic field lines and the motion, the rotation of the coil are 90 degrees to each other, then EMF will be produced. EMF will be produced. Okay. Then we say the induced EMF is greatest. It will be greatest at maximum position. When we say greatest, meaning the peak value. The induced EMF will be at its peak value, will be greatest when the coil is horizontal, the coil, or parallel with the field. Parallel with the field lines, as in the position it cuts through the field at the fastest rate. Okay, you say the induced EMF is greatest. That means will be at its maximum position when the coil is horizontal or parallel with the field lines, as in the position it cuts through the field at the fastest rate. Now the EMF is smallest when the coil is vertical or perpendicular with the field lines, as is in the position it cuts, or it's not cutting, as in the position it will not be cutting through the field. Okay, at this point, when this slippery commutator is here, this hole, this split, once it's here, then there will be no what? Contact. At that point, the induced EMF will be smallest, maybe zero, will be at zero on the graph, or negative value. Okay? Now let's take a look at it. Say the induced EMF is smallest means zero when the coil is vertical. When the coil is vertical or perpendicular to the field lines, as this position will not be cutting through the field lines. Okay, I think this is a bit contrary. You say when it's vertical, it will not produce field. When it's horizontal, I think they mix this. Mixing this point up. Okay, anyway, let's see from what they have. Maybe we get a better view. Now here is the magnet, right? We see the magnet. This is the north, and this is the south. This is the north. This is position 1. This is the north. This is the south of the magnet. Okay, and then this is the coil. These ones are the coil. Okay, these red ones are the coil, and this is the magnet. This coil, you see, they are in 90 degree with the orientation of the magnet, right? 90 degree with the orientation of the magnet. Okay, so at this point, when rotation continues, when the field, the magnetic, the rectangular array is rotating, when it's rotating, at this point, when it's very fast, when the speed is very high, it produces the highest value of the peak at position number 2. When the magnet will now be like horizontal, the magnet will be in this form. The magnet will be in a horizontal manner. When the magnet is in horizontal manner at this point, and the field, these are the coil, then here we have the greatest value. Okay, when the magnet and the coil are in this horizontal orientation, then we have the magnet maximum field. Then at position 3, when the south of the magnet is not facing up, the north is facing down, and in this orientation we are back to 0. You know, here was 0, this is 0 of the graph. This bottom one is the negative side of the graph, this bottom side. This is the negative side of the graph. So at the beginning like this, when the magnet was standing like this, we have 0. Okay, we have 0, even when the coils were in this horizontal manner. But when the magnet was now rotated to be in this manner, the magnet is now in this manner with the coil, okay, producing a magnetic field in this manner, which is 90 degree to the orientation of the coil, like I said before, 90 degree, which is 90 degree to the orientation. You can see the magnetic field, 90 degree to the orientation of the coil, And this is the coil, orientation, horizontal. The magnetic field is vertical. So when, at this point, we get the greatest value. Okay? At position number 2. We get the greatest value of the induced EMF or the induced voltage. We get the greatest value at this point. Now, at this point, we get back to 0. Why? The magnet has been produced to be in a vertical manner now. The magnet is now in a vertical manner. But the north pole is now down and the south pole is up. So the fields are going in the same direction as the coil, both horizontal. When we have both the field and the coil in the same horizontal manner, we have 0. We have 0. The effect produced will be 0. Because there will be no induced EMF when the magnetic field and the coil wire are in the same horizontal array. When they are both in the same horizontal array, there will be no magnetic field. It will be 0. Now at the position 4, when we now have the magnet rotated to this side, the south pole is now to the left, and while the north pole is to the south, we have a greatest minimum value. The greatest minimum value, a negative value. Okay, greatest minimum value at position 4. So this is what is taking place when the magnet is in position 1, as shown, this one, this position 1. When the magnet is position 1, you can see the magnetic field. They are along the coil. Then the induced EMF will be 0. Induced EMF will be 0. Okay? We say when the magnet is in position 1, and then the magnetic field lines of the magnet do not cut the coil. The magnetic field do not cut the coil. You see? Magnetic field lines, they're going horizontal like this. They're going horizontal, right? The magnetic field are going, and the coil are also going horizontal. So they don't cut the coil. If they don't cut the coil, what happens? 0. You will not produce any voltage or current. Because the Faraday's law says that for induced EMF to be produced, the magnetic field lines that are produced must be like 90 degrees, must cut across as in position 2. You can see that, you see the magnetic field line is cutting across the coil. It's moving across the coil. Okay? It's only when at 90 degrees, you can see if you put the 90 degree sign here. At 90 degrees, it's cutting across the coil. When it cuts across the coil at 90 degrees, then it's only then we produce EMF. And you can see the greatest value when the orientation is like this. When the orientation is like this, you get the greatest value. Okay, at position 3, it's also put in a way, okay, that the magnetic fields are now parallel to the coil. If they are parallel to the coils are the red one, the red lines. If the magnetic field, this arrow, they are parallel to the coil, then the value of the induced EMF is again back to 0. You know, this is the 0 origin, the origin of the graph, 0 value at this point. So when you rotate it or turn it again, rotate it to another one. This one is like 0 degree rotation, 90 degree rotation at position 2. At position 3 is 270 degree rotation, and at position 4 is 360 degree rotation. So at 360 degree rotation, we get the greatest minimum value. At 0, we get 0. At 0 degree rotation of this magnet, we get 0 induced EMF. At 90 degree rotation, we get the greatest value. At 90 degree rotation, we get the greatest value, which is this. At 180 degree rotation, which is semicircle, 180 is semicircle. At 180 degree rotation of the magnet, we get 0. We also get again 0. So at 0 degree, we get 0. At 180 degree rotation, we get 0. Then at 270, we get greatest minimum, and then at 360, we get 0. We get back 0. So this is the 4 rotations you get when your coils are rotating or your magnets are rotating in a magnetic field. And this gives the kinds of induced EMF that is produced. So at this point, it means if it doesn't cut, if the coil or the magnet does not cut across the coil, then this means that there is no EMF induced at position 1. At position 1, there will be no EMF because the magnetic field does not cut across the coil. So it does not obey Faraday's law. So if it does not obey Faraday's law, magnetic field do not cut across coil, then there will be no EMF produced. Now at position 2, as we've said already, the magnet in position 2, the magnetic field of the magnet are 90 degrees to the coil. Now this means that there will be a maximum EMF induced in the coil. Look at it. At position 2, there is now a 90-degree rotation. Something that was vertical like this is now horizontal. The magnet is now horizontal. The magnetic field produced is the one that is vertical. The magnet itself is now horizontal. Are you with me? The magnet itself is now horizontal. So producing a magnetic field that cuts across the coil, 90 degrees across the coil. At that point, we produce the greatest maximum value. We produce what? The greatest maximum value of the induced EMF or induced voltage. At position 3, look at position 3, it's now back rotated vertical. The magnet is now vertical, producing a horizontal arena, producing a horizontal magnetic field, which are parallel to the coil. Since it's parallel to the coil, it does not move across it, there will be no induced EMF. So the induced EMF is against 0 on this axis. It's against 0. The induced EMF is 0 here at this point. So it's 0 because the magnetic field does not move across the coil. In order to produce current or induce EMF or induce current, alternating current, this magnetic field must be moving across like this. If coils are going horizontal, the magnetic field must move across it. Like in the case of position 2, you see the way it's moving across it? It's moving across it. This arrow is showing magnetic field lines. So it's moving across it. But this one is not moving across, it's moving along. So no voltage is produced, no current is produced, nothing is produced, is 0 here at this point, which is the 0 origin. So at this point is again the magnet has rotated to another 270 degree rotation, and then you see the greatest minimum. Why we call it greatest minimum? Because it's at the negative side. Okay, induced voltage is induced, and that's why you see the galvanometer deflect to the other side, the negative side. This galvanometer now deflect from here. You know this is the 0 pointer. Okay, it deflect the pointer. This is the pointer, this arrow. So at greatest minimum, it goes back to negative side, this negative side. Okay, for the first 90 degree, where you have the greatest maximum, it deflects to the positive side. That's why you have this one. It deflects to the positive side. That's how you have this. Okay, at 270, when it deflects to the negative side, when its greatest minimum value, it deflects to the negative side. Okay, so this is what is shown in the galvanometer, the value, what is produced. Okay, let's move. I think we've extensively looked at this one. Okay, I think we have a question here which we can take a look at. We say the diagram below shows a simple AC generator. When the coil is in the position shown in the diagram, the output voltage is plus 10 volts. Okay, complete the table below showing the output voltage for the different angles of rotations of the coil. For the different angle of rotations of the coil. Okay, so at 0, the voltage was 10 volt. At 90, the voltage is 0. At 180, the voltage will be negative 10 because this for voltage. Okay, at 270 to be 0, again, at 360 will be plus 10. Okay, now it says we should complete it. So at 0, what do you have? We have 10. At 90, okay, I think this is done. Is this why, or they want us to rearrange it? This, okay, I don't know if you can hear this one. Let's see.
Let's start by reading through the question and then having a look at what we have to do to answer this one successfully. The diagram below shows a simple alternating current or AC generator. When the coil is in the position shown in the diagram, the output voltage is 10 volts. Complete the table below, showing the output voltages for the different angles of rotation of the coil. So how we're going to read this is our very, very simple AC generator. So this coil is going to rotate about a central axis. So these parts are going to 90 degrees, is going to rotate up, so it's going to be standing straight up. At 180, it's going to be flipped over. 270, it's going to be standing straight up again. And 360, it's going to look exactly like this, because then it's completed one full circle, and there's 360 degrees in a circle, which I hope you remember from mathematics. So what have we got? We've got a max output voltage of 10 volts. I need to fill in the rest of the output voltages for all these different angles of rotation. These have not been chosen randomly. They've been chosen very specifically. So if we remember what alternating current looks like, it produces a graph that looks like that. Now, we've got current, but I'm asked for voltage. They are proportional, so the alternating voltage graph will look similar to this. The size will be different, but it will have a similar shape. This graph starts off with 0 current. My graph starts, or my setup here starts with 10 volts. So I'm just going to modify this ever so slightly. So I'm saying it's starting here at 0 degrees, and at 0 degrees I have a reading of 10 volts. That's what I've been told in the question. The first step I'm going to go is to 90 degrees, and that is where that 90 degrees occurs, where the graph cuts the y-axis. I have 0 volts at 90 degrees. At 180 degrees, I'm at the minimum value, or the maximum negative value, so that's going to be minus 10. The next step is 270 degrees, and then I'm crossing 0 again. And as I said before, 360 and 0 is actually the same point. So that's going to be back up to 10 volts because it's done one full rotation of the circle. So there's the table completed for the different angles of rotation, showing the different voltages that we'd get at those parts of the cycle.